So today I'm going to give you all an overview of error mitigation, what it is and how the techniques we use work. And then we're going to move into transitioning from research into product, and Blake will talk about performance capabilities we use for evaluating performance benchmarks that we use for evaluating these capabilities. And then Andrew will close out the session by talking about the efforts we've put into improving the performance of our stack and how you can use these tools in your own work. And if you haven't had a chance to yet play with this, with the Qiskit code assistant, please give it a try. Here is a relevant example to the methods I'll be discussing today, specifically probabilistic error amplification. And we've had a limited set of training data for this, so if you have feedback, this is something we'd really appreciate a lot. Okay, so over the last couple of days, we've been talking about how you can run utility-scale workloads. You heard from our partners about the tools they're building in our Qiskit functions catalog, and how you can use the transpiler to optimize circuits on our hardware. And finally, today, we're going to talk about the last piece, right? How can you get accurate results from existing noisy quantum computers using methods like error mitigation, right? And essentially, this is the question we've been asking ourselves for the last several years, and I think you'll see why this is important, right? What can one do with quantum computers even before we have fault tolerance, right? And to build some intuition for this, I want to walk you through a very simplistic example. Okay, say we had one of these 5K circuits with 100 qubits. Okay, and let's assume for a moment that all of these gates were at the at the best numbers that we have, about 3 nines, 99.9% fidelity. Now, if you tried to estimate what is the fidelity of the state you prepare at the end of the circuit, that's going to be a very small number, about 70 minus 3, right? That gives you some sense of how accurate that final state you would prepare with a 5K circuit at this level of performance. Now, one can ask, well, is there something useful you can do when these state fidelities are that lousy, right? Now, if we want to preserve that quantum state, well, one needs quantum error correction, okay? And we have to encode this information into a large network of qubits, so you have the physical overhead of qubits. But then one can ask, instead of actually trying to preserve the state, is it possible to ask the question of, can we estimate certain properties of the state accurately, despite that state being so low fidelity? Okay, and to further build some more intuition for this, this is one example I really like to talk about often. Let's imagine that we had about 100 different spins, all in and then they're all magnetized in the same direction. So you have 100 spins, all pointing up. And if you asked what the uniform magnetization is, normalized, that's 1. Okay. Now, if there was one small error that flipped one of these spins, and I asked what the overlap is, well, the fidelity is now 0. Okay. But if I asked instead, what's the average magnetization of these spins? So sorry, this network of 1,000 spins, right? The average magnetization is only going to be wrong in the 3rd digit, right? So perhaps fidelity is more of a worst case metric, right? There might be certain quantities that we can actually extract if there weren't too many errors, okay? And so basically, when we want to execute quantum circuits on existing hardware, maybe we want them to be short depth, okay? We don't want too many errors to accumulate over the course of the circuit, right? So that we might have interesting signal we can play with at the end to actually produce accurate results, even though the fidelities might be very low, right? And the depth of these circuits, the number of parallelized entangling operations we have, this can only keep getting better as the hardware gets better, okay? So this has really been the essence of our roadmap, right? That over the next 5 years, we want to keep increasing the number of operations we can execute in these circuits and still continue to get accurate results from these pre-fault tolerant quantum computers. Okay? And then the other piece is going to be error mitigation, right? You have signal, but then you want to take that signal and then actually report something that's accurate, something that you might have got from a noiseless quantum computer, right? And I'm going to talk about two methods that were invented at IBM, probabilistic error cancellation and zero noise extrapolation. And just to give you some very quick, a quick introduction to these methods, in probabilistic error cancellation, we're typically executing many different circuit instances with additional gates inserted to effectively reconstruct the inverse of the noise channel. And in zero noise extrapolation, we're also inserting gates typically to amplify the noise. And by remeasuring expectation values at amplified noise rates, we want to use that to extrapolate back down to the zero noise limit. Okay? So the three main ingredients in all of this is typically one needs to characterize the noise in the device, and then we want to manipulate the noise once we have a sense of what that noise is, and we want to manipulate it in a way that we can effectively undo its effect. Okay, and this isn't such an alien idea, right? I mean, even in our classical devices, our noise-canceling headphones, our telephones, some of these principles exist. That we have some sense of what the noise is, and we do some things to it, and then we effectively undo its effect, right? So let's take the example of circuits of this nature, where we have certain layers. This is the ideal circuit. We have certain layers of parallelized entangling operations. That's what you see in these blue boxes. And now when you execute this on actual hardware, well, the circuit's going to be noisy. And so you can model this as, for each of those layers, you can model this as a noise channel and the ideal unitary, right? And then we basically have to try and characterize these noise channels. And this, in general, is an extremely challenging task, right? Because to compare, to be able to characterize this completely, one needs an exponentially large number of parameters, right? About 4 to the 2n. So trying to do this on a 100-qubit device is practically impossible. However, there's some tricks that one can do. You can shape the noise in a more convenient form to a polynoise channel, and you'll learn about these things in a session later today. With things like polytwirling, you can reduce this complexity to 4 to the n. Okay? So this is still an exponential, right? And it still doesn't completely solve the problem. So one eventually has to make some assumptions. One has to make an assumption of sparsity and locality of the noise. And by doing that, on a 100-qubit device, you can then reduce the number of parameters you need to learn from 10 to the 80 or something down to a couple thousand. Okay? And this makes this much more viable. Okay? I'm not going to go into a deep dive of how this learning is done, but you will hear a lot more of this in our seminar 2 in the error mitigation deep dive. Okay? And of course, a natural question one can ask is, well, is this noise model truly representative of the device noise? And that is going to have a significant impact in the accuracy of the error mitigation. Okay? Particularly for those of you who are familiar with running experiments on hardware, right? One thing you might be very familiar with is that, well, the T1 times fluctuate over time, right? If the T1 times fluctuate over time, the noise model is going to fluctuate over time, right? And as one executes utility scale workloads, you have lots of qubits. All these different qubits can have their own fluctuating dynamics, and this can get very complicated very easily, right? And this was why we highlighted at the State of the Union this really important capability that we have in our new herons, the ability to mitigate the effect of these defect 2-level systems that really lead to these fluctuations in coherence. Right? And here is an example that we have, and I have the archive link up there as well, of how over 2 days we can really stabilize these noise models. And this is going to be a very important capability for us as we want to more reliably execute large workloads with large numbers of qubits. Okay? Right. So essentially, once we have access to this noise model, the typical thing to do now is to insert gates, right? And that's what you see those single qubit gates flipping on the screen. We're going to insert these deliberately, and they're going to be sampled based on the learned noise model, okay? So we're going to try and insert these gates And this, we do this to effectively amplify the noise, or if we account for the science, we can also effectively cancel the noise, okay? So this is going to be, what's going to be common over the two methods I'm going to talk about. The first I'm going to focus is on zero noise extrapolation. And once again, okay, just to give you a very quick recap, the ingredients are we want to learn the noise, which we can, making assumptions about locality and sparsity of the noise. Once we have that, we want to manipulate it. We want to amplify the noise. We can do that by deliberately inserting these single qubit operations based on that learned noise. And then once we have measurements at different amplified noise levels, we want to extrapolate down to the zero noise limit, right? And this is an example of this methodology in action, right? I won't go into the details of what particular circuit was run here. I'll just tell you that there is some observable that we want to measure. We know what the ideal answer is. It's supposed to be 1. Because we have noise, when we run the circuit at the base noise level, that's the G equals to 1, you have some bias from the ideal result, a bias of about 20%, right? Now, we can run many circuit executions going up to about 2,000, intentionally inserting single qubit operations to effectively amplify the noise. Okay, we effectively amplify the noise by a factor of 1.2, 1.6. So now we have 3 sets of data points at the base noise level, at 1.2, 1.6, and we can use these 3 to now extrapolate back to the zero noise limit, right? And we can use an exponential function here, and we actually see that we do very well with the extrapolation getting very close to the right answer. So this was basically the machinery that led to the utility experiment, okay? What we showed here was that we could run 127 qubit circuits going up to a depth of 15, and we looked at increasingly complicated correlation functions. We asked, what is the evolution of the average magnetization of this kicked this kicked icing model? And then we asked some more, we chose to look at some more complicated correlation functions with increasing weight. And in all these 3 cases, because of special aspects of the problem, despite this being beyond the scale of brute force classical computation, we were able to access what the ideal results should be, okay? And this had to do, for the experts in the audience, this had to do with light cones, okay? This had to do with the fact that even for these observables, there were a limited set of qubits that actually play a role in the accuracy of these correlation functions, okay? And in all these 3 cases, we were able to see that the experiment with error mitigation, with probabilistic error cancellation, zero noise extrapolation, was able to produce accurate results. This, we argued, was evidence for the utility of quantum computing before fault tolerance, okay? And to give you some more sense for that, I want to focus on the last part of the experiment that we did in this work, which was pushing the depth even further, pushing the depth out to depth 60, where we were now beyond exact verification. We couldn't play these light cone tricks anymore, right? And soon after the experiment, well, there was a lot of attention from classical simulation experts all across the world. And I want to show you some of the data from all of these different methods. Right? You might have seen some of this at the State of the Union as well, but essentially, operating now at a scale beyond exact verification is a game that's being played out, which has essentially been the game that classical simulation experts have played for decades. You don't know what the exact answer is, and you need to compare between different classical approximations, okay? And in there is basically a variance of about 20%, and you don't know which is the right answer, okay? Now, what I haven't told you actually is one of those data points was from the quantum computer, okay? So now we can begin to play this game with a quantum device. We're able to play this game with a quantum device with error mitigation, where at a scale beyond brute force classical simulation, we're able to produce reliable results. Results that compare with other classical methods. And these were all the other classical simulation experiments there. So this was an experiment at 2,800 gates approximately, right? And then we had our roadmap. We promised that we're going to extend this out to 5K next year on our Heron processors, and we announced on the first day of the conference that this is what we did. With the same method, with probabilistic error cancellation, we ran these mirrored versions of the kicked Ising circuits in the utility experiment. This was because even though we're at this non-trivial scale, by mirroring the circuit, you still know what the right answer is, because the circuit's now going to be identity equivalent at the end. But we were able to execute this at the 5K level. We were able to get very good accuracy. 60% of those weight one observables were beyond the 10% threshold. But as I emphasized at the State of the Union as well, what was really important here is that this can now be run by all of you. Okay? This can be run by all of you. The same utility experiment can be run by all of you, and it can be run 50 times faster. And we'll hear more about this in this seminar. Okay? So we were able to do 5K with probabilistic error amplification. I want to now switch gears to probabilistic error cancellation, which was the second method. So the essence is quite the same. It's really more of bookkeeping of some science. Once again, you learn your noise model, you know what terms are there in it, and you want to intentionally insert single qubit gates to basically mimic the effect of the noise model. To cancel its effect, you do some bookkeeping, you take care of some science, and now you can effectively cancel the noise in your circuit. Okay? Or at least you can in principle have observables that you measure which are noise-free. And this is a really powerful method. Unlike zero noise extrapolation, where you don't have guarantees on the extrapolation, here, if you had a truly representative noise model, you can essentially get unbiased estimates. Okay? And what this formalism really enables is basically an ability to quantify a runtime to solution. You can essentially quantify how much time will it take for you to execute a noisy quantum circuit with n qubits with a depth of d, and produce unbiased expectation values from this, right? So what you see here is beta times d. This is essentially the runtime of executing the circuit. And d is the circuit depth, and then you have an exponential in there, the gamma bar to the power of nd, right? That gamma bar is essentially some measure of the device noise. Okay? And n times d is going to be the circuit volume, right? And so, this can potentially be very troubling that, oh my God, there is an exponential runtime in there. And is there anything we can do? Well, the game that we're trying to play with error mitigation is to try and drive that gamma bar closer and closer to 1. Okay? Approximately, this goes as 1 plus epsilon, where epsilon is the error rate, the 2-qubit error rate on the device, approximately. Okay? So smaller that epsilon, the closer you get to 1, and that's going to enable larger and larger circuit volumes. Okay? So, yeah, one can always then ask, well, is exponential scaling always bad? Is exponential scaling always inferior to polynomial scale? Right? Well, in the asymptotic limit, yes, it is. Things are going to blow up exponentially, but then one has to ask the question, how do these compare in more practical settings? In the kind of settings we're interested in over the next 3 or 4 years, right? Going from 5K to 15,000 gates, right? So let's just look at this very, very simple example, okay, of 2 functions, one an exponential, one a polynomial. Let's try and put some numbers in there. So maybe for an epsilon of 0.01, loosely, this could be thought of as maybe your error rates, and then x very loosely can be thought to be your number of qubits, right? So if I compare these 2 functions, for the exponential scaling, you get 3. And for the polynomial, you get this ridiculously large number, right? So this really highlights that when we compare the scale, when we compare different methods, and we ask the question, well, is exponential always bad? Are there efficient classical methods with polynomial scaling? It's important to consider how these compare at practical settings. At this limit of 100 qubits, depth 100, or even beyond, right? At the scale where one is already beyond what one can do with brute force classical computation, it's very likely that you might have circuits you can execute more efficiently on a quantum computer despite this exponential scale. Right. So this is essentially what's driven this vision towards 100 by 100 and beyond. You can basically ask now, what is going to be the sampling overhead from probabilistic error cancellation as you want to increase these circuit volumes? And you can put in some numbers and see how feasible this is, right? And basically what you'll see here is, as your 2-qubit error rates dip below 1e minus 3, you will have an overhead of about 10 to the 8 circuit executions for the PEC piece alone, right? And you can also see the effect of the exponential improvements in gate fidelities, right? As your error rates drop, these runtime overheads are going to come crashing very quickly. And so this also points to now speed. How quickly you can execute these circuits also becomes very important. Because if you want to execute 10 to the 8 circuits, well, if you had a sampling rate of a kilohertz, that's going to take about a day of runtime, right? In the State of the Union, we also highlighted the improvements in error rates, in our latest Heron processors compared to the 2023 utility experiment. And even there, we'd highlighted that, this 5x improvement is going to have a tremendous impact on the kind of error mitigation sampling overheads that we have, right? And you can see I have some numbers at the top. Essentially, that PEC sampling overhead for a 100 by 100 circuit drops by 70 orders of magnitude with this 5x improvement in gate fidelities. And we already know our best fidelities are even better, closer to 7.5 E minus 4, so that's going to get the overhead even down if we can have a large device at that quality. Okay? This is the essence of our roadmap. And I'm really excited. This is data fresh off the oven, but this is basically 40 qubit data going up to a depth of 8 of probabilistic error cancellation, okay, in action. Right? On here, what we're looking at are mitigation of observables, not just 1, not just 2, not just 3, the way we looked at in the utility paper. This is looking at observables all the way going up to a weight of 40. Okay? This is what it means to have an unbiased error mitigation technique, that almost independent of the circuit complexity, almost independent of the complexity of the observable that you want to mitigate, you're able to produce an accurate result for practically any observable. Okay? You really are able to do things which you might have been able to do if you had a noiseless quantum computer. Right? And as those error rates drop, those volumes are going to keep increasing. Right? Excellent. So I told you about zero noise extrapolation. I showed you the latest from our experiments with probabilistic error cancellation. I now want to talk about another very important emerging area, right? The use of classical HPC to extend the reach of error mitigation. This is also incredibly exciting, right? This is work from our group here on shaded light cones. And essentially, this was something I alluded to even in the utility experiment, right? Where observables might only be dependent on a fraction of the gates in the circuit, right? And here it's highlighted in the yellow, right? So what this means is that even if one had noise on the gates in blue, those don't impact the observable. What that means is perhaps you don't need to pay a sampling overhead cost for those gates, okay? So that trivially becomes a reduction in sampling overhead, which can be quite significant as you try and execute large circuits. Right? Now one can further ask, even within that light cone, are there certain gates which don't have too much of an impact? Okay, and this we're going to call the shaded light cone. And now accordingly, depending on the impact of certain errors in certain parts of your circuit, you can choose where to sample more and effectively invert the noise and so on. And this you can do using classical HPC, right? And by doing that, you can reduce the sampling overhead by orders of magnitude. Okay, so this is going to be a very powerful technique. From our partners at Algorithmic, we heard about tensor network error mitigation. Matteo spoke about this on day 1. This is also a very exciting technique, right? Typically, the goal is to apply, to execute some ideal unitary U, and we want to measure an observable at the end O, okay? This is not what we have access to on current hardware. We only have the ability to execute a noisy version of that U. So that first block can be remodeled as something like this, where you have a noisy version, its inverse, and the ideal block again. And once again, you're asking that this effectively ideal block, on this, I want to measure this observable O, right? Now, if I divide this up, you can basically try and backpropagate the observable O across those latter two blocks, and now ask the question, can I execute a noisy version of the U that I was interested in on the quantum hardware and estimate this backpropagated O prime, okay? And that's going to be equivalent to executing the ideal circuit U and measuring O. So how does one access O prime from O? Well, for that latter bit, you can essentially execute that using tensor networks. You can execute that on classical HPC, right? And then, well, someone could ask, okay, if one could execute or simulate this on classical HPC, why would you use a quantum computer? The thing to notice here is that in the limit of low noise, that U dagger inverse, the U tilde inverse U, that block is very close to identity. So it's very likely that that block in the limit of low noise might be classically simulable, even though U in itself might be hard to simulate, right? So this is a very powerful example now where all of the error mitigation is now taken off into post-processing and can be run on a classical computer. So this was a method proposed last year. This year we had this very exciting collaboration with them and with John Gould's group at Trinity College Dublin, essentially applying this method to circuits up to 91 qubits with a depth of 91, right? And here once again we played this utility game. We first ran this on classes of circuits which have special analytical solutions. These are called dual unitary circuits. And you can read more about this at the link on the slide, right? So there, we were able to see that in the absence of error mitigation, we had this quickly decaying signal. That got much better once we applied this error mitigation. And once we had confidence in the device, our modeling of the device noise, and the error mitigation techniques, we were now able to perturb away from these parameters where one had analytical solutions and operate now once again at the scale where we're beyond brute force classical simulation and can only compare to classical approximations, right? So we compared to a couple. With one of them, there's tremendous disagreement. With one of the classical approximations, we do pretty well. And at this scale, we don't explicitly know what the exact answer is. Okay. So you're going to see more and more examples of work like this, right? This is a game, as I'll reiterate, this is a game that classical simulation experts have played for decades. We can now begin to do this with a quantum device. This is why these devices now are tools for scientific discovery. Right. We're going to see more and more examples of problems like this as the devices get better, as the devices get faster, as we have a wider range of error mitigation techniques, many of which are going to be available through Qiskit functions. Okay. Switching gears a bit now, I want to talk about advancing algorithms, also using classical HPC in a framework we refer to as quantum-centric supercomputing. Many of you are already familiar with this because I think you had a challenge on sample-based quantum diagonalization. Expectation values are not the only kind of useful signal you can get from existing devices, even from samples that you can run, that you access from these devices. You can actually do very, very interesting problems. This has really enabled scaling up chemistry by far faster than I imagined. We had some of these initial variational quantum eigensolver experiments in 2017, and these were all stuck at the 6 to 20 qubit level. And it really blows my mind how fast this area has emerged. And already we see, this is an example of Fe2S2, I believe with 45 qubits. And basically with the linear extrapolation of the quantum data, we were able to see that the values you get already begin to compete with really state-of-the-art classical methods, right? So this is really a powerful direction that leverages the best of quantum and classical HPC, right? This experiment, when it was published, had about, I think, up to 3.6K 2-qubit gates in the circuit. And then the State of the Union, we showed that these kinds of things could also be extended to 5K gates, right? This was for the example of hydrogen chains. And basically, these are also methods that are accessible now through Qiskit add-ons. And we were able to benchmark this against mean field methods and basically see that as we have hardware improvements, we're going to get closer and closer to classical state-of-the-art. Right. So I gave you examples of these error mitigation techniques, PEA, PEC, TEM. We spoke about SQD. How can you now get the most out of these quantum computers at this utility scale, running computations beyond what one can do with brute force classical? Right? Over this entire process, we've really been working to make all of these different tools accessible to you guys in Qiskit. On day one, you heard about TEM and how that's accessible through algorithmic circuit function. We also heard about KEDMA and other error suppression techniques from Q-control. These are all methods you can leverage. SQD and others like backpropagation. These are all methods that are accessible through Qiskit add-ons. And altogether, as we begin to develop these techniques in research, our constant endeavor is to push this into product, to make these available to you, our users, right? You can use PEC and Xeni in the Qiskit runtime primitives. And these techniques really set many of the requirements in our stack, both for speed and quality, right? And to evaluate how well these capabilities are performing, we need benchmarks. We need to be able to benchmark how well these capabilities are working. And for that, I'd love to welcome now our next speaker, Blake Johnson, to talk to you about benchmarking these. Thanks so much.